I've had a couple questions about Lab 5, sections 5.1 to 5.4, which looks like this. Now, this is the circuit that has the comparator with hysteresis in front of an integrator, and that circuit is from figure 20-35 in the textbook. And just to give you a quick review on how that works, the first part of this circuit over here, this is the comparator with hysteresis. So this is a comparator. You will note that it has positive feedback in that the feedback resistor goes back to the positive input. And what that means is that a little bit of a change on this output here, if this goes up by a little bit, then the positive input goes up as well. And then that will make the output go up even further in the positive direction, which will make the input go up a little bit more. So what happens with positive feedback is that as soon as this input, as soon as this point here is a little bit greater than 0 volts, then the output will fly off up to the maximum positive value, which in our example is going to be 15 volts. So the output of this circuit is essentially plus 15 or minus 15, and it is a square wave. That gets fed into this point right here, and there you can see the diagram saying it's a square wave. That gets applied to the integrator circuit, and the integrator, what happens is plus or minus 15 volts at this point generates a current, and that current flows into the integrator circuit. It cannot go into the input of the op-amp, cannot go that way, so it has to go around and it charges up this capacitor. A little bit of it goes through R4, but typically what you do is you make R4, make this guy like 100 times R1, that guy, R3, make it 100 times R3, and so very little current goes through there. Most of it goes into charging up the capacitor. So we're putting current into this capacitor here, and essentially if there's 15 volts here and 0 volts here, then we are essentially charging that capacitor with a current source. And if we charge a capacitor with a current source, then what will happen is you will get a constant rise in voltage. If you put constant current into a capacitor, the voltage will rise at a constant rate. So you will get time and you will get voltage. And so coming out of the integrator, you will get a triangle wave. So this goes high, that goes to the negative input, so this starts going low until it pulls this point down, until it pulls this point down below 0, and then this goes low, and then this goes high, because this is an inverting op-amp. So you will generate an oscillator here that basically has, you could tap off of this point here, and you have a square wave, and you can tap off of this point here, and you have a triangle wave. And they've provided you with some formulas here, but I'm going to show you how to figure out these formulas without memorizing them. And that's essentially what I'm doing here, is I'm trying to lead you through, in my example here, I'm trying to lead you through the calculations in a manner that basically helps you develop the formulas without memorizing them. So the first one says, what is the integrator input current? So as we said, at this point right here, on the output of the comparator with hysteresis, this voltage is going up to 15 volts. And when it goes down to minus 15 volts, because the op-amp has, it's powered by plus 15, minus 15. So we're assuming that the output transistors on the op-amp turn completely on, and they saturate, and we get a good 15 volts out. So a little bit of an assumption there on that. So when this goes up to plus 15 volts, current will go in through R1 here, Since this point is held at 0, the op-amp will hold the output so that the negative input stays at 0 as well. So no current will flow into the input of the op-amp because that's an open circuit. So what happens to the current is that the current has to get diverted around and it's used to charge up this capacitor. And since we're charging it with a constant current, it will charge, the voltage will rise at a constant rate. So I've kind of got some formulas over here on this section here. So we start off, there's 15 volts here, and then there's I in. How do you calculate I in? Well, I in is going to be equal to V in over R1, which is a 1K. So it's going to be 15 volts, the output from the comparator, over 1K. You're going to get about 15 milliamps going into that capacitor at a constant rate. So that is the first answer here. Integrator input current, when the output of U1A is a high voltage, 15 volts, you should get about 15 milliamps. Then the next question is, well, what's the charge rate of the capacitor? How fast does the voltage rise on the capacitor? And for that, we're going to use this fundamental formula for capacitors, which is that the current into a capacitor is equal to C dV dt. I think you've seen that in physics, and I know I've mentioned it in semi-dev, and I mentioned it again here. So I of t equals C dV dt. This is how a capacitor works. So what you would do to figure out the charge rate is we would take I of t equals C dV dt, and I would rearrange that to get dV dt on one side and I and C on the other side. What you end up with is 15 milliamps divided by 1 microfarad. You do that division and you come out with a voltage rise rate of 15 kilovolts per second. So on this integrator, when we have an output, when it is going up at 15 kilovolts per second. And then when it hits the top, when it hits the upper trip point and it also falls at 15 kilovolts per second. Which seems like a lot, but when we do the calculations, further calculations, you'll see that it's not that excessive. So 15 kilovolts per second is what should go into this capacitor thing. What is the charge rate of the capacitor? It charges at 15 kilovolts per second. Now the next question here, it says, well, what are the U1A? So what are the trip points of the comparator with hysteresis? And we're looking for the upper trip point and the lower trip point. Now the way that you calculate that is you ask yourself, so here I've got a 10K ohm resistor, and here I've got a 33K ohm resistor. So when the output is high, what I would do on this is I would say, let's set the output high to plus 15 volts. We know that the comparator is going to toggle when this point here, when the positive input goes above or below 0, because the negative input is 0. So when this positive input goes a little bit above or below 0, that's where it's going to trip. So what we've got is on this side of R4, we've got a connection to 15 volts because the output is the upper transistor is turned on and it's high. So here this is 15 volts. I got 33K ohms. Looking into the input of the op-amp, this is an open circuit, so it's essentially not connected to anything. And then I've got a 10K ohm resistor, and then on the other end of the 10K ohm resistor, I've got a connection to I don't know how many volts. This is what I'm trying to figure out, is I'm trying to figure out what voltage here will cause this to be 0 when this end up here is 15. So I'm going to redraw that circuit, which I've got over here. So one end of the 33K is tied to 15 volts. We want the center point to be 0, and then I've got a 10K. So what voltage down here will get me 0 volts in the middle. So in order to do that, what I would do is I would figure out the current through these resistors, and then I could figure out what this voltage is. So the current through the 33K ohm resistor, this point is 0, this point is 15 volts of the 33K, 45.5 microamps. So that current is flowing down here. It cannot go that way because that's an open circuit. So it must continue to go down through the 10K, which creates a voltage drop across the 10K. And that voltage drop, there's 45.5 microamps going through a 10K. That means that the 10K will have 4.55 volts across it. And since this end is at 0, that means that this end here must be at minus 4.55 volts in order to get 0 in the middle. That is our lower trip point. Alternatively, when this is negative 15 volts, then this would have to be positive 4.55 to get 0 in the middle. So this is our upper trip point. So now we've calculated the upper and lower trip point. So what's going to happen is the output from the integrator will rise up to 4.55 volts, and it will trip the comparator, and then it will drop down to minus 4.55 volts. So the change in voltage from minus 4.5, basically the voltage between these 2 points, it's 9.1 volts. So the output of the integrator has to rise 9.1 volts, and it does that at 15 kilovolts per second. So we can figure out the rise time. Let's take a look at the rise time here. We know that the change in voltage required is 9.1 volts, and it's 15 volts per second. You can do a quick little thing here. If you want to make sure you're on the right track, what happens if I divide 9 volts by 15 kilovolts per second? Well, that becomes 9 volts. Since over here I'm dividing by a fraction, that's the same as inverting the fraction. That's the same as inverting the fraction and multiplying. So a voltage times seconds over a voltage, the volts cancel out, and what you're left with is seconds. So 9 volts over 15 kilovolts per second comes up with 0.6 milliseconds. That is strictly the rise time. We also need the fall time. The period is from here to here. Periods between those 2 points. So the total time is the rise time and the fall time. That's going to be 1.2 milliseconds. When I invert that, I get the frequency 833 hertz. So the upper trip point should be 4.5 volts, 4.5 volts. Rise time should be 0.6 milliseconds and 0.6 milliseconds. That gives you a 1.2 millisecond total period and about 833 hertz frequency. Okay, I think the last question was, well, what happens when you put this into Multisim? Does it work in Multisim? So if you enter this into Multisim and you press the Go button, what you end up with is a triangle that looks something like this. I'll see if I can pause it at a good point. So here's the triangle wave coming out of the integrator. So I'm lining this one up with this peak, and I line this up with this peak. I come down here and I got 1.35 milliseconds. That compares pretty well with our calculated estimate of 1.2 milliseconds. So it looks like our understanding of this circuit is pretty close. And like anything in electronics, There's always a little bit more to it than that. We're modeling the circuit using some pretty basic rules. If we got a little more accurate, we would probably get closer to this value. And what would be one of the things that is more accurate? Well, this point here doesn't actually go up to 15 volts. It might be up to 13 volts. And that means that it charges a little bit slower. And if it charges a little bit slower, then the period would be a little bit longer. So maybe when you're doing your calculations, try it with 13.5 on the output. There's not a lot of current that comes out of here. So it should be able to rise pretty quick, or it should be able to get close to the output. So try redoing the calculations with 13 volts or 13.5 volts and see how that compares to our simulated values. So that's it for that example. If you have any more questions, feel free to ask.